electron volts. There are some indications, for instance, that the neutrino mass scale may not be very small, that these have to be confirmed. For instance, from the Boss experiment recently, they have been claiming that they see the neutrino mass is the sum of all neutrino masses at 3 electron volt at about maybe 3 sigma, 2 to 3 sigma, but that's not yet confirmed. So still I'll say that the neutrino mass scale is not known. In neutrino oscillation, we only have the differences of the squared masses. And if you look at the absolute scales here, the neutrino masses are really tiny compared to the masses of the other fermions just done. That's also some puzzle to understand why these masses are really smaller than the other masses. And of course, since we have here only the square difference of the masses known, so there are in principle two possibilities that the masses are ordered, which one calls normal mass ordering, or there are two possibilities where the masses are kind of ordered, which correspond to the two sides here, the dimensions. The M3 may be the lightest, or the heaviest of these neutrinos. And if the M3 is the lightest, that's called an inverse neutrino mass ordering. If the M1 is the lightest, this is called the normal neutrino mass ordering. And if you fix one of the masses and you say that the absolute neutrino mass scale is pretty large, then it turns out that actually the splittings between these masses becomes much smaller than the masses themselves. In this case, one talks about the quasi-degenerate neutrino spectrum. So this is what people are normally distinguishing. First thing is when you have the masses here, M1, M2, M3. This here is the neutrino masses. And this will be a normal neutrino mass ordering. Or in this case, when the M1 is much larger than the others, people speak of a normal neutrino mass hierarchy. So the other possibility is that you have the M3 is the largest, and then we have the M1 and M2 are actually pretty close together already. When you solve for the two masses from this measurements, fixing the M3 being the lightest, and you have a reverse hierarchy. The third possibility is if these masses are all pretty large, then they are all three very close together. This is called the quasi-degeneracy. And at the moment, it's not clear which of these neutrino mass spectra is actually realized in nature. Okay, so we will come to possibilities how to realize this spectra also a bit more in my third lecture. Okay, now coming to the mixing angles. We have the definition I've already mentioned, but here it's again shown. So one can parameterize them as a 2-3 rotation matrix times this complex 1-3 rotation matrix, which has the mixing angle θ13. So S13 is sine θ13. E to the minus the delta, and this delta here is the so-called Dirac CP phase. We have the same for the PMS matrix and for the CPL matrix. Apart from this piece here, if neutrinos have Majorana masses, and if that's I will come to, then there are two extra phases in such a diagonal phase matrix here. But these at the moment are not known. Whether neutrinos have Majorana Dirac is not known, and so these phases are also not known at all. We have some information about these parameters here. Of course, in the quark sector they are well known, and in the neutrino sector we have information from neutrino oscillations. Okay, so that's what it looks like at the moment, what we know. So first looking at the quark sector, we have the 1-2 mixing is about 13 degrees. That's the Cabibbo angle, which is the largest mixing angle in the quark sector. And the other two angles, they're actually quite tiny. So the 2-3 mixing 2.4 degrees, and the 1-3 mixing 0.2 degrees, so they're much, much smaller than this 13-degree mixing angle here. Well, there's another puzzle. If you look at the measurements that have been done in the neutrino cycle, neutrino oscillations, we know that actually there's one mixing, the θ13 mixing, which has been discovered by the Dyer experiment, the Dyer Bay experiment mainly, is about 9 plus minus 1 degrees, so it's kind of this size as this 1-2 mixing in the quark sector, but that's the smallest mixing angle here. So all the other mixing angles are much larger. So the 2-3 mixing angle, it could even happen that it's really maximal, or the 1-2 mixing angle is well, about 34 plus minus 1 degrees. So it's also very large. It's not that this is not maximal, but kind of two large mixings and one, we say, quite small mixing of the order of the size of the largest mixing that we have in the quark sector. So big difference in the mixing in the neutrino sector and in the quark sector. And that's another puzzle. Why is there such a big difference in these mixings? And here we have measured the CP phase, about 70 degrees in the quark sector. And here the CP phase is not yet known. It's not yet known if we have here the Majorana neutrinos and the masses, of course. But the values, of course, also not known. So that's the situation that we have for the mixing angles. And of course, one challenge is to understand all these differences. This will be the main topic of the third. So there are altogether a lot of issues in the Standard Model that are not resolved. And I think one of the clearest ones of them is are the neutrino masses. So as we mentioned, neutrino masses in the Standard Model is a renormalizable theory. You cannot even write them down. If you say the Standard Model is an effective theory, then you can write them down. But you have this scale here introduced, which is the cutoff scale only until this year. The effective Standard Model can be used. Above this scale, one has to replace this by a fuller and more complete theory that generates this effective operator. So we also know that new physics has to be there, has to be introduced, and this is kind of missing in the Standard Model. So the other challenge is data structure that I've already mentioned. So why are the masses on hierarchical for the charged fermions? Why is there so large mixing in the neutrino sector? We have the gauge hierarchy problem, which is the stability problem of the Standard Model. Then we have additional new scales introduced. And for instance, if this scale here is quite high, close to the magnification scale, for example, then you explicitly introduce such a scale in your theory. It means you have very explicitly a hierarchy problem, an instant integration of your Standard Model. I'll also come to this a bit more in the second lecture when I talk about connections to grammar. Okay, and then also when you relate more to cosmology, we of course have the fact that dark matter is present, is the largest, is a much larger part of the matter component of the universe, and it should be some particle, which is not one of the Standard Model particles. So it's an extra particle. Again, it may be even connected to neutrino physics, but definitely one would have to introduce new physics to account for that. Well, the present acceleration may be due to new physics. Another interesting thing is that the flatness in isotropy that we have in our universe today points very much at cosmic inflation, and even more so the recent PISA-2 results would indicate that there is an earlier stage of inflation, and there should be a particle associated with this, which is also, unless you modify gravity in a certain way, none of the Standard Model particles. So you need an inflating particle, which is again something beyond the Standard Model. And finally, we have the matter-antimatter asymmetry in the universe, which is the fact that we all exist here are made out of matter, whereas in the very early universe we expect the matter-antimatter to be created in the same amount. So at some point in the evolution of the universe, we would like to generate this whole abundance of matter over antimatter. And in order to do this, you also need more than the Standard Model. So to improve the Standard Model is not enough to account for this barrier asymmetry. So a lot of reasons to know the Standard Model, and I think neutrinos is one of the most direct, very key aspects that it has to resolve. And maybe it's connected to all these other things, or some of the other things, the other issues. Okay, so now let's become a bit more specific and go to the possibilities for neutrino mass mechanisms. Okay, so before I really go to mechanisms, I would just like to fix a bit notation with you. There are a few preliminaries on the spinner. The spinner notation. So what you know probably, and that normally dealing with is a 4-component spinner psi here. So it has some upper components and some lower components. So these two components are wild spinners, so kind of 2-dimensional spinners, and they are actually representations of S and 2C. For the upper one, we're kind of fundamental representation of S and 2C, so the universal covering group of the Lorentz group for the upper component, and this here is a complex conjugate transport closed representation of S and 2C. So these two sort of wild spinners, they make up a 4-component spinner, psi here, and here also I've just put together some of the convention here in the wild representation. These are gamma matrices, and in particular gamma 5 here has this form, and this the gamma 5 one can do projection matrices that relate to the where I can project the upper and the lower components. So these are the projection operators I just mentioned to you. So they're constructed here, and if you go back, so the gamma 5, so the gamma 5 is this matrix here. So you can see that the left projection operator projects on the upper components. And if I write down a spinner, psi L, what I mean is this is the left projected 4-component spinner. So just remember this is an object which has only one spinner degree of freedom, and namely it's a fundamental SU2 spinner, maybe this upper component here. On the other hand, psi R is a right projected 4-component spinner that only has the lower components. Okay, and then the other spinner operations, so you know the Dirac adjoint is making the following here. Out of this 4-component spinner, so it's basically flipping upper and lower components, or the names here. So you have here that psi becomes the complex conjugate, and the lower component, the chi, becomes the upper one. And similar also this charge conjugation matrix is basically complex conjugate. This transforms spinner into fermion into its anti-fermion, and converted the Dirac adjoint. So the Dirac adjoint is an extra transpose of this. Okay. So what I want to do next is to develop with you which different types of neutrino masses one can actually construct. And this will be very important to keep this overview and distinguish these possibilities. So is my watch correct that I already spent 40 minutes? Okay, so I have kind of 10 more minutes, right? Yeah. I think in order to use a bit less time, I think I will proceed here with my premises. Namely, the thing is the following. So you have now going back to this right projected and left projected spinners. So the right projected are these lower components, the left projected are these upper ones. You have two possibilities to form 4-component spinners. One is you basically just put them back together again. This means adding the right projected and the left projected, and you recover what you had before. So it's kind of a full 4-dimensional spinner with independent upper and lower components. This is called a Dirac spinner. Right? But you also have the possibility to fill up all the components here just by using one, for example, one left projected spinner. So you take the left projected spinner plus the left projected spinner charge conjugate. So what you're having here is you have again all components filled, but you're using the same degree of freedom in both cases. When you do this, then what you have is called a Majorana spinner. And you can check that when you have the Majorana spinner into the charge conjugate transformation, then you kind of end up with this Majorana spinner itself. And this is not, nothing else than a statement that you may have heard very often, that a Majorana particle is its own antiparticle. So if you can describe a particle which is such a Majorana spinner, then doing the charge conjugate operation, you end by itself. So that's why, if neutrinos could be described by only such a spinner, then they would be their own antiparticles. Okay, so these are different types of spinners. Now, more explicitly, what you have to look at is whether the particles now have Dirac mass terms or if they have Majorana mass terms. So this is basically describing their properties. So if you have a Dirac mass term, then it would look like this here. This is basically what you have known from your electric particle lecture. You have a four-component Dirac spinner, Dirac adjoint times the spinner, so it's the mass times the right part, Dirac adjoint times the left part, plus the emission conjugate. So it connects always the left chiral and the right chiral component, so the left projected and the right projected element of the spinner. So interestingly, now we look, that would be invariant under some U1 transformation like this here, when you transform both left and right chiral parts by such a U1 transformation, and the diagrammatic representation would be this here. So actually, this here is, for example, lepton number that you can use for neutrinos. So if neutrinos would have only this mass term, you would have a remaining lepton of this. Okay, but then there's another possibility, namely that you write down a Majorana mass term in the same fashion, but using this Majorana spinner that we've just introduced. Something like this here. So if you write it out, it looks like this. You're connecting not a left and a right chiral part, but you're connecting the left and the left charge conjugate part. Okay, this here would be not invariant under such a U1 symmetry, so you would violate lepton number when you have such a mass term. And diagrammatically, you would represent this here by some clashing errors. So such a mass term actually you can view as kind of an interaction given by this cross here. And then as you do the normal Feynman rules, you have particles which run to the vertex, the particles which are here in the Lagrangian are not complex conjugated, run to the vertex, and this would be here. So you have 2 times complex conjugated, both kind of standard representations, they both run to the vertex. This would be these clashing errors. These clashing errors indicate also this lepton number symmetry is broken. Okay, and then the third case is maybe one which is very interesting for neutrinos also, is that you can also have both. You can consider the situation that you have as well a Dirac mass term as well as a Majorana mass term. So this here is the Dirac mass term. This connects left and right chiral components here. And this here are Majorana mass terms. And now here for both. So we have to say here for the right chiral part, for this degree of freedom, and for this degree of freedom, we add for both of them Majorana mass terms, connecting the field with the charge conjugate, or the complex conjugate with the charge conjugate. And then what we would have is a mass matrix like this here, for these 2 degrees of freedom, for the left chiral and the right chiral charge conjugate. And this, if you want to go to the mass eigenstates, you have to diagonalize this. So you get 2 masses which look like this here. And in fact, the mass eigenstates would look like this, where this kind of rotation angle can be read off from this matrix in this form. So it's probably the most interesting situation is that you have one of them, well, for example, this M left Majorana mass matrix is 0, And the Dirac mass matrix is much smaller than the mass matrix of the right. Degrees of freedom, and that will be the Caesar mechanism, which I will show you again in the next transparency in a bit more detail. But what is also interesting to look at is when you now go back to this mass matrix and say that actually here both of this left and right Majorana masses would be 0, then what you would recover is a standard Dirac spin, right? So we only have Dirac masses. And in fact, what this means is a Dirac mass is nothing else than basically 2 Majorana spinners with the mass plus n and minus n. So this is basically if you have 2 Majorana spinners with the same masses, just one negative, one positive, you can also combine them and put them back into Dirac spinner. So the general case actually that we have Dirac masses and Majorana masses, no matter what they are, you can diagonalize them, and the eigenstates would be 2 Majorana spinners. So the Dirac spinor case is basically, the Dirac mass term case is basically just a special case for this. Okay, but now back to the Caesar mechanism. That's the situation when you say that you have here a Majorana mass matrix for the white color fields, whereas which is much bigger than this Dirac mass part here. Okay, then you can diagonalize this, and you get for the light mass eigenstate, this has a mass of the order Dirac mass squared over m right, and the heavy eigenstate would be of the order of the kind of this matrix element here, m right, and you can now see that the bigger this Majorana mass gets, the smaller the mass of the light neutrinos gets. And this is represented here in this famous seesaw picture. So if you have a very heavy guy here, a very heavy lighter neutrino, then you can get a lighter and lighter mass of the standard model light neutrinos, so which in this case is basically mainly the standard model light eigenstate. So the smaller mixture of this white kind of thing. And this here basically now connects back to this picture. So we have here this mass eigenstate of new physics, which we call lambda. So this kappa was proportional to 1 over lambda, and this would be basically to the right kappa of degrees of freedom here. They are not contained in the standard model. There would be some extra degree of freedom, which comes in with a new mass scale, in this mass scale m right. This would be the scale of the physics here. And the mass that we get would be a Dirac mass squared, so this is of the order of the electric scale, divided by the scale of the physics, namely the mass scale of the right color neutrinos. And I think my time is practically how much? Oh, I have 50 minutes. Okay, very good. Okay. So then I can come to the second part that I wanted to discuss with you. Namely, now getting again one step more explicit. Namely, to discuss explicit extension of the standard model. So we discussed, in order to generate this operator here, what we have to do is we have to introduce a new physics. But now we can be more systematically, and we can think about which new physics we can actually introduce. Okay? And there are, in fact, it turns out there are 3 possibilities that one can generate neutrino masses by just a tree-level extension of the standard, just a tree-level realization of this effective operators by very simple extensions of the standard model. And you can think of this in the following way. So you have your fixed field, you have your leptons, and then you basically want to resolve this effective vertex here by introducing a implicit field. What you can do is you can do it basically this way around. Yeah. So the question is, what is this extra field x here? Or do something else. Maybe you can do it this way around. Here are the leptons. then you can do it this way. Okay? So this would be an extra scalar field that you have to add. And this here would be an extra fermion that you would have to add to the standard model. Okay, so the first possibility is the one which we have already encountered in the discussion of the last section, namely, is that one can add to the standard model a right chiral singlet field. So this would be this possibility. So we have here, this here is a doublet on the SU2 left. Right? This here is also a doublet on the SU2 left. And the big hypercharge, if you add this two here up, is 0. So this would be a complete singlet that one can exchange here. And that's this field. So, and this is normally called a right chiral retrieval. But it is a complete singlet under all standard model symmetry. Okay, now if you have this, you have the standard model Lagrange, and you have to add, or you can add, these new terms. And these are basically all the new terms that you can add that are allowed by symmetries. You have a kinetic term, you have here a Yukawa coupling and a Majorana master of the right-hand retrieval, or of these singlets. And when you do this, you get exactly what we discussed before. You get the Caesar mechanism, which, when you go to matrix form, has this result here for the neutrino mass matrix. This is called the type 1 Caesar mechanism. Okay, so this is exactly diagrammatically what you have. You interchange here this heavy field, basically in this way, and this could be called a triangle. So kind of in these two channels, when you integrate all of the theory, these heavy right-handed neutrinos, then below the mass scale of the right-handed neutrinos, you can describe everything on this effect. Okay, possibility 1. Possibility 2 is also kind of obvious, because you know when you have two doublets under the SU2 left, then the product representation, 2 times 2, you can reduce to a singlet, as we just discussed, plus a triplet. So the other minimal extension of the standard model, just logically, is to do the same thing, but not having a singlet here on the SU, a singlet fermion plus a triplet fermion. So you can have a triplet representation on the SU2 left, which you exchange just like this here, or as we've seen for the singlet. You have to kind of respect here the rules how to contract doublets to triplets. So this is this transformation here, basically. This is this product here, for instance. And then you again write down all the terms that are allowed. And what you get is again kind of a Caesar mechanism. It has a very similar formula than for the type 1 Caesar, but it has different phylogenical consequences because you don't have a singlet, you have a triplet. You have a field which is not charged under the gauge symmetry. So that's called the so-called type 2 Caesar mechanism. So, excuse me, this is called the type 3 Caesar mechanism, if you have this fermions. Okay, the third possibility, the logical one, is this here. So when you have these two doublets here, you can contract them either to a singlet or to a triplet. But if you want to contract them to a singlet, then the two contractions of these doublets here is anti-symmetric, so you can never get mass terms for the neutrinos. So this is not a marginal possibility. But the other one remains. You can contract these doublets here to an SU2 triplet. And this is this extra field here, delta L, which you can introduce. It's a triplet, it has these 3 components here. You can again write down all the mass terms and kind of couplings terms that you can have that are allowed by the standard model symmetries. So again, a very simple extension of the standard model. And what you get is, again, neutrino masses, which are now proportional to this kind of left of this SU2 left triplet field. So the small VL times the Yukawa matrix. That's basically from this coupling here, where you couple 2 left-hand doublets to this triplet. And if the neutral component here gets of F,